Great. Hi, everyone. I'd like to welcome you back to Mathematics for the Impatient. We're here with Stan Kladko. We have an interesting topic this week. We're going to be talking about security. I'll start off with the first question, Stan. Can you tell us why network security is important for proof of stake networks, and how do hackers typically hack those kinds of networks?
Yeah, that's a great question, Marcus. To understand why security is important, let's just first talk about what we discussed already last time, that proof-of-stake networks are great because in particular, they don't actually waste energy. You know, like Bitcoin and also Ethereum version 1, they actually use lots and lots and lots of energy, and people want to move to proof-of-stake networks to be able to reduce this energy use. But on the other hand, proof-of-work networks, they are pretty secure because they do number crunching. And to hack a proof-of-work network, the hacker has to have computational power, which is comparable to the power the good guys have. So this computational power requirement actually limits hackers. So for Bitcoin and for Ethereum version 1, we see literally nowadays trillions of dollars being secured and hackers not being able to hack. Now, for proof of stake, things are different. There's no number crunching in proof of stake. The difference is that for proof of stake, you have cryptographic algorithms, cryptographic keys, you have complex networking protocols, and all these things together, they actually provide security and allow you to forget about number crunching. The bad news is that the proof of stake networks, they are more complex, they require 10 times more code, they require more experienced engineers, and as a result, potentially they are easier to hack because the code is complex and people are humans, and every human usually makes mistakes. You know, some people make mistakes every 1,000 lines of code, some people make mistakes every 10,000 lines of code, but it's really hard to produce a human that will be perfect. So it's very natural that a complex system, complex software, always have bugs, and some of these bugs are security relevant, meaning that hackers can actually break the system using those bugs. And this actually explains why many of the hackers are teenagers, because teenagers have lots of time. And if a particular software system has a bug in one particular line of code, well, teenagers just have time to try everything and find the bug. And then for proof-of-stake networks, if you break into the system, you can steal cryptographic keys, you can make money transfers, you can sign some messages, you can artificially, even for a particular validator, make this validator look bad or malicious. So this validator gets slashed, and the investors that actually delegated this validator lose money. So if a hacker is able to break into a networking node, a networking computer, many bad things can happen. And hackers usually try to stay anonymous. So the typical thing that happens is that the hacker is somewhere on the surface of this planet. You don't know what the hacker is. The hacker actually connects to your system through many intermediaries. So you don't actually know the source address of the hacker. And then the hacker pretty much just tries to do everything until the system is broken. To give you a good analogy, let's say you have a wall. You have a huge wall. And then somewhere in this wall, there's a weakness. But to find the weakness, you need just to examine and knock and try to break in different places in this wall. And then if you break in a single place in a wall, the entire wall becomes useless. That's the very specific asymmetry that attackers have versus defenders. If you defend a wall or if you defend the computer system, you have to make sure everything is perfect. And if you're an attacker, you just need to find one single hole. And then the entire protection, the entire wall becomes useless. So because of this very specific asymmetry between attackers and defenders, it's so hard to protect computing system. And in reality, every computer system is breakable. The question is only how much investment and how much expertise you are willing to actually use to break the system. So if you want to secure your system, you can never do it perfectly. You can only aim to raise the bar for the attacker. So it will take more money, more effort, more expertise for attacker to break your system. And that's actually what we are aiming for at Scale.
Cool. So I know, testing network security is incredibly important, right? It's something that you've got to make sure that you're doing on a regular basis. There is a very cool technique called fuzzing. So I wonder if you could kind of take a little bit of time and tell us what is fuzzing and how can it be used to prevent network attacks?
Yeah, fuzzing is actually a pretty interesting technique. And it's actually, the idea is that you actually do what hackers do. We just discussed teenagers that have lots of time, right? How teenagers break into computing system? Well, they have lots of time. They try this, try that. They try different attacks, different responses. So basically, they're trying kind of randomly to break into. To give you another analogy, let's say you want to get accepted into a particular university. So you send one application letter, it doesn't get accepted. You send another application letter, you tweak this, tweak that. But it's also very important for you to see the response. If you see that the next application letter gets you further, for instance, you send one application letter and you are rejected like immediately, and you send another application letter and you are rejected 7 weeks later. So you would actually conclude that the second one was probably a little bit better because it probably got through more stages and it got rejected at a later stage. So that's pretty much the idea behind fuzzing. It's not like just you're sending totally random things to the system. You're sending something and you're checking the response. Sending another thing, you're checking the response. And you're trying, by judging the response, you're trying to intelligently tweak what you are sending to get more through the system. So that's pretty much the idea of fuzzing. It's not just, you could take a computing system and just randomly try to send anything to it and break it in any ways, but it would actually take you lots and lots of time. But you could also take your computing system and try doing something to it and seeing the response. And then from the response, you are trying to guess how deep you got inside. And by making small tweaks and different directions, you will actually ultimately be able to break into the computing system. So fuzzing is actually a white hacker technique because it requires the source code. So you run your computing system, you have your source code. So, and then you're sending some random things to it. You're literally trying to break this wall in random places and knock on different, places on the wall just randomly. But let's say you knock in one place on the wall and you hear a different sound and you conclude maybe there is something, maybe this place is better to try to break in. And then you knock harder or you knock in a different way. And every time you measure how deep you get inside. And although on every single step, you don't actually break in totally, you actually break in deeper and deeper and deeper. And your hope is that at some moment, you will actually break total protection. The entire system gets broken. And that's pretty much the idea of fuzzing. You're a white hacker, you're actually trying to find vulnerabilities in your system. So you're running your system in a special mode where the system, every time someone tries to get in, the system measures how deep was this shot, how deep the attacker got in. And then you tweak, and you usually tweak randomly, but you try different directions. And you always choose the direction where you actually getting deeper and deeper and deeper. And through the sequence of steps, turns out that because computers are so powerful, they can try so many different combinations. So by trying this is literally zillions of combinations intelligently and measuring every time how deep you got and tweaking randomly at every step, you essentially creating this model. You can also think about this as about like evolution. You think about surviving, and the survival means actually getting deeper. So this kind of evolutionary model or random model actually allows you to break into the system. And that was fuzzing is. And it turns out that fuzzing nowadays is a pretty established subject in computer science. And people fuzz different things. People fuzz cryptographic libraries, people fuzz networking systems, people fuzz things like hardware chips. So it has become a pretty significant field of computer science and pretty successful. It turns out that you actually can, by doing fuzzing, you actually can find vulnerabilities in your system. And if you can find vulnerabilities in your system before hackers find it, you guess what? You can actually fix it. So you always have this competition with hackers where the security of your system actually depends on how fast you find holes in your own wall, essentially, and you patch those walls. And that's what is fuzzing about, and that's what's so exciting. And so good projects like Ethereum, for instance, they've been using fuzzing. Some other people have been using fuzzing, and it's really, really interesting technique.
Very cool. So I mean, I guess my last question would be, how is SKALE using fuzzing to more effectively protect the network?
Yeah, that's actually a really interesting story, and it's also a story about community. So fuzzing was always on our plate, and as every startup, you always, focus on something. So when you start, you develop a prototype, and then you turn this prototype into a product, and then you're starting to secure the product and harden it and do all kinds of security analysis. So that's a typical set of stages for a startup. So that's what was on our plate. And we were about to actually start doing fuzzing on our own resources, so to speak. And then by exactly the same time, we found out that there were some people essentially on GitHub, and that's the beauty of GitHub, that everything is open. And these people just got interested in our code, that in particular got interested in our crypto and our SGX wallet. And just of curiosity, these people, there were several really great guys from several universities in Germany, and they just fuzzed our SGX wallet, and they found a problem in our SGX wallet, and they reported this problem to us, and we issued them a bounty and fixed the problem. And then guess what? Several weeks later, another person comes, again from Europe. Maybe we'll get more submissions from other parts of the world, but this person was again from Europe. And this person fuzzed another part of our product, and also just out of curiosity. And also, we provided to this person a grant, a SKALE token grant. So far, we didn't actually get to fuzzing ourselves because we have these great people in the community doing the things for us. And actually, fuzzing is a very specific subject. Some people fuzz networking, some people fuzz, chips, some people fuzz crypto. So just from the community, we're getting this great input that we actually don't even have to fuzz our thing, other people are doing it. So now we actually have two groups, to both of which we are issuing SKALE grants that will do fuzzing. And actually, we hope that we will never have to do it ourselves. If any of you guys can do fuzzing, if you are interested in helping SKALE, please let us know, because we at SKALE are much more willing to actually work with the community than do things ourselves, because we're a small team. But having said that, we're also looking to using some fuzzers internally, some networking fuzzers. And the work is doing really, it's a big direction for us. And we are really pushing into this direction. And the reason is that it makes things much more secure. For instance, SGX wallet was already secure. We discussed this in the past. It was already much more secure than just storing secret keys on a hard drive. Now we have these great people who actually did fuzzing on it. They found some weak places, we fixed those weak places. Now we know that we've been fuzzed, and it's actually working much better. So every single step we do to help secure our product is great, and there will be much more fuzzing in the future, and we will be establishing more ties to academia, because as I mentioned in the past, it's a very interesting research subject. So for you guys, if you're interested in fuzzing, please contact us. If you are interested in securing your proof of stake network, you can actually take many things from SKALE that have been fuzzed already, and they are pretty secure. In particular, our SGX wallet could actually be used for other networks or for other security products. And if someone wants to actually secure things in your particular software or in your particular open source product, please use SGX wallet. It's nowadays a pretty secure piece of software.
So I think that the end result is come check things out. You can join our Discord, which is scale.chats. You can also see all of our code. We're all open source up on GitHub. And thanks, Stan, for the latest.
Thanks, Marcus.
All right,
Great
take
talking
care.
to you today.
Bye.